So now we talk about stereoisomers, and stereoisomers can be subdivided into conformational isomers and configurational isomers. When we talk about configurational isomers, we have again a subdivision into E and Z isomers and isomers with chiral centers. And now we talk about conformational isomers. And conformational isomers means that we have rotation around the carbon-carbon bond, and the two isomers can interconvert rapidly at room temperature into each other, because for this conversion from one isomer into the other, it is not required to break a chemical bond. So there's a free rotation, and that's why this conversion is quite easy. In contrast to this free rotation, we have for the configurational isomers no easy conformation from one into the other isomer, as we need to break a chemical bond. And so if we now look a bit closer into conformational isomers, we can, for example, take ethane as molecule. And here we have a carbon-carbon single bond, the sigma bond between the two carbon atoms, and then we have on both sides of this sigma bond only hydrogen atoms, and as you can see here, we can easily rotate the molecule along this sigma bond, and thereby we change the position of the hydrogen atoms in space. And of course, we can also talk about more difficult molecules where we do not only see hydrogen atoms attached to the carbon atoms where the rotation takes place. And especially then, if you have, let's say, more difficult molecules, it is easier to draw the molecule in a different way so that we can directly see what the rotation induces in terms of position of the functional groups in space. And therefore, we use normally the Newman projection for a better visualization. And here you can see this Newman projection for the ethane molecule. And in general, we then talk about the so-called staggered conformation and eclipsed conformation, which are the two, let's say, extreme conformations of this molecule then. And the staggered conformation is the more stable conformation, as then all hydrogen atoms or functional groups are as far as possible apart from each other. Conversely, the eclipsed conformation is less stable, as you can see that you have an interaction between hydrogen atoms, which are now quite close to each other. And if you want to draw this Newman projection, you always start with the carbon atom, which is closest to you as a point. And then you draw the carbon atom, which is as far as possible apart from you, as a circle. And then you have a so-called dihedral angle, which is now in the staggered conformation at 60 degrees. And this is the angle between the carbon-hydrogen bond on the front and that on the back carbon atom. And this angle is also called the torsional angle. And you can see that in the staggered conformation you have a dihedral angle of 60 degrees, whereas in the eclipsed conformation this dihedral angle is 0 degrees. And we can then more or less say that this dihedral angle determines the energy of the isomer. And here you can see a plot of the relative energy of the conformation versus different dihedral angles. And we have again ethane as example, we start with the eclipsed conformation, where we have all hydrogen atoms as close as possible to each other, so we know this is not energetically preferred. Then we can go to the next conformation, the staggered conformation, where we have dihedral angle of 60 degrees. And now it is important, as we only have hydrogen atoms in the molecule, that we have a look on the different colors so that we can see which hydrogen atom is on which position. Because always, if we go from one conformation into the next, these hydrogen atoms will change their position in space. And here you can see then we rotate further, then we go again to another eclipsed conformation, and if we continue rotating, then we end up in another staggered conformation. Then we go again to an eclipsed, staggered, and eclipsed conformation, which is then the starting point again. And the staggered conformation is always more stable, as we have lower energy in the system, because we have less repulsion of the hydrogen atoms compared to the eclipsed conformation. And we have the so-called torsional strain of 12 kilojoule per mole, which is required to convert one conformation into the other. And this torsional strain can also be called energy barrier to rotate. And important here is that you always have in mind that there is a small energy barrier of here, for example, 12 kilojoule per mole, but this energy barrier is quite small, and so this rotation can easily be done at room temperature. And if we now go to a more difficult example, where we do not only have hydrogen atoms, but also other functional groups, we can have a look on butane. And this molecule seems to be more difficult, but the principle is the same as for ethane. So again, we have the different conformations where we can rotate the molecule along the carbon-carbon bond and then see different conformations depending on the dihedral angle. And now it is important that we have a look on the central carbon-carbon bond, where we have then on the first carbon atom a methyl group, as well as on the last carbon atom. And around this bond we then rotate. And again, we have intervals of 60 degrees of dihedral angles. And what is now new, we have the so-called syn, periplanar, and anticlinal conformation, which are both eclipsed conformations. And then we also have two types of staggered conformations, which are called anti-periplanar and clinical or gauche conformations. And these two types of conformations are always dependent on the relative position of the methyl groups to each other. And this is the only difference. And then the rest is similar to ethane. So we have the staggered conformations, which are lower in energy due to the lower torsional strain. And hence we can say that the staggered conformations are more stable. And now the only difference is that we have two types of eclipsed and staggered conformations, which have different energies. And this you can easily see here. If you just follow the energy diagram, then you can see that the lowest energy will be here in the anti-periplanar conformation, where you have the methyl groups as far from each other as possible. And here you can easily see that the two methyl groups are very close to each other, so you will expect a repulsion, whereas here in the anti-periplanar conformation, the methyl groups are quite far away from each other. And similar to the examples of ethane and butane, the conformations of cycloalkanes are also determined by torsional strain and steric strain, but now additionally also by the so-called angle strain, which can also be called bias strain. And here it is important to remember that the carbon-carbon-carbon bond angle in cycloalkanes is normally 109.5 degrees, which is preferred for sp3 hybridized carbon. And if this is not the case, then we talk about the so-called angle strain. And as example, we can have a closer look on cyclohexane. And here we see the chair conformation, and we have 6 carbon atoms, and on each carbon atom we have hydrogen atoms, and ideally these hydrogen atoms want to go into the preferred staggered conformation with the lowest energy. And here we can differentiate between 2 different types of hydrogen positions. The first position is called axial position, and the second equatorial position. And for cyclohexene, we have 3 hydrogen atoms above the ring, 3 hydrogens below the ring, which are all in the so-called axial position. And here you can see the example. So axial means you go up or down. And then we have also the equatorial position, where they are in equatorial conformation, and there we have 6 hydrogen atoms being in the plane with the ring. And so we can say that each carbon atom has 1 equatorial and 1 axial hydrogen when we talk about cyclohexene. And they can change the position. We're so-called ring flip. And here, for cyclohexene, for example, it doesn't really matter, as we have only hydrogen atoms and no other functional groups in the molecule. But as you can imagine, for example, if you have, instead of a hydrogen here, for example, a methyl group, and then you do this ring flip, it does matter then in terms of energy. And then what is important that you think about, the space which is available in this position. So when we have an axial position, we have less space and therefore more strain, whereas in equatorial position, we have less steric strain. And the reason for this is that we have more space available. And if you have a look on the table, then you can see that if you have only hydrogen atoms, you have a probability of 50% for hydrogen being in the equatorial position at room temperature. But then for the larger groups, for example, already for the methyl group, you have a probability of 95% already. So this clearly shows that if you have larger functional groups, then they would always prefer to go into the equatorial position, because there you have more space for these larger groups. And then, of course, we can also have a look to the Newman projection, and it is very similar to ethane and butane. Again, we have the fact that it is best to go into the staggered conformation when we talk about the Newman projection, because then we have less repulsion of the functional groups. And then of course here it is briefly shown how you can draw the Newman projection also for cyclic molecules. And what I would like to suggest now is that you think a bit about this 3D model, and if you're totally fine, then it's good, and if not, you can just make your own 3D models and turn, and then you can see how the functional groups interact with each other, in which position this helps maybe to better visualize what is going on in this molecule. After talking about conformational isomers, we now go to next type of stereoisomers, which are called configurational isomers. And configurational isomers can then be subdivided into E and Z isomers, as well as isomers with chiral centers. And when we talk about configurational isomers, the important point is that isomers have, again, the same molecular formula and the same type of bonds, but in contrast to conformational isomers, the configurational isomers cannot easily interconvert into each other at room temperature. And configurational isomers mainly occur in disubstituted alkanes, as there is no rotation around the carbon-carbon double bond at room temperature. So we can have two substituents which are either on the same side of the double bond or on the other, or the opposite side of the double bond. And the two isomers can then be separated from each other, and they have different physical properties. Some of the configurational isomers even have different chemical properties. So if you have alkenes, we have one sigma and one pi bond, and hence the rotation around the carbon-carbon bond is blocked. For example, we can have a look on butane. Now we know that the rotation about the carbon-carbon bond is blocked, and we can see here we have two methyl groups on the same side of the carbon-carbon double bond. Then we have the molecule which is called cis-but2-ene, and then we could also have the two methyl groups on the opposite side of the carbon-carbon bond, and then we would have trans-but2-ene. And as you can see, the cis and the trans configuration has a different boiling point, so we know that cis and trans alkenes have different physical properties. And if you want to bring one into the other, then you definitely need to break a bond. And then another important point related to this cis and trans configuration is the so-called Kahn-Ingold-Prelog rules, which are also known as SIP rules or priority rules. And there you have nomenclature for the E and Z isomers. And cis and trans is still okay, but now it is preferred to call the so-called cis isomer better as E isomer, and then the trans as Z isomer. And related to this cis-trans isomerism, we use the Kahn-Ingold-Prelog rules, which are also called SIP rules or priority rules, where we refer to the higher priority groups for assigning then the E and Z nomenclature. And now you might be a bit confused. So we have cis and trans and E and Z. And it is so that we now prefer to stick to the EZ nomenclature, but cis and trans is also still okay. So if we have the SIP rules, then we always start to look at the carbon-carbon double bond. Then we go around to all substituents and check which has the highest priority. And then if we see that the substituents with the higher priority are on the opposite side of the carbon-carbon double bond, then we have an E isomer. And if the higher priority substituents are on the same side, we have a Z isomer. And here I would like to give you an exercise for naming the molecules according to the priority rules. And I would say I do the first example together with you, and then you can continue with the other examples by yourself. So if we now want to assign the E and Z isomers, then we start at the double bond and then we go around to check which priority is for which a substituent. And the bromine has the highest ordering number in the periodic table, and then we know already this is a high priority substituent. And then we go further, and we know that carbon has a higher ordering number than hydrogen. So we know that the next highest priority should be either this or this substituent, because we go to a carbon atom. And then we know that the methyl group has only one carbon atom but 3 hydrogen atoms, whereas the ethyl group has 2 carbon atoms. So that means we have then the second highest priority here, then the methyl group as third priority, and the hydrogen atom as first or lowest priority. And then we know that the bromine and the ethyl substituent are on the opposite direction of the carbon-carbon double bond. And that means that we have an E-isomer. And this isomer is called E2-bromopent2-ene. And yeah, then I would say now you can do this exercise, and later on in the slides you can check if you're right, and if you figure out that you have problems, you can then ask in our question section.